Vectors in the plane 6.3, day 2. Today we're going to start and talk about unit vectors. There are many times when we'll find that it is useful to find a unit vector that has the same direction and as a given non-zero vector. So in other words, a vector that doesn't start at the origin and it's not a zero vector, but it is a unit vector and it has the same direction. Sometimes that's a very useful piece of information that we need. To find a unit vector, you can divide the vector by its magnitude. So the formula looks like this: unit vector, and they're represented by the letter U, is equivalent to the vector itself divided by its magnitude, which is also equal to 1 over the magnitude of the vector times the vector. Therefore, the vector itself becomes the scalar. Remember, I told you a scalar was a number that was, and in this case it will actually be a vector itself, but it's a value that is a multiplier. It's a multiplier. That's primarily what it does. All right, we're going to note a couple of things that are important. We're going to note that the unit vector is, that U is the scalar multiplier. We're going to note that U, the unit vector, is the scalar multiplier of the original vector, and that vector U has a magnitude of 1 in the same direction as vector, the original vector. All right. I'm going to move on a little longer. The vector U is called a unit vector in the direction of V. So the unit vector basically is the unit vector. It's in the same direction as the given vector V. All that makes more sense when we have some applied information. So let's look at an example. We're going to use the example of finding a unit vector. All right, so let's say we're given the component form of vector V as -2, 5. To find the unit vector, we would have the original vector divided by its magnitude. In this case, the original vector in component form is -2, 5, and it would be divided by the magnitude. Remember, magnitude is its length. We use the distance formula. We've already done, in component form, we've already done part of that distance formula, so it would be the square root of -2 squared plus 5 squared. And we would get 1 over, and I'm going to go ahead and rewrite this as 1 over, the square root of this is the square root of 29 times the vector 2, 5. So this 1 over the square root of 29 becomes our scalar, which is a multiplier to both the -2 and the 5. And our unit vector then would be equal to, in component form, -2 over the square root of 29 and 5 over the square root of 29. Now, you know Ms. Zorn would really prefer you go ahead and rationalize those denominators. I'm not going to do that in this example, but that would be my preference. All right, let's move on. All right, let's continue. Let's talk about the unit vector 1, 0, and 0, 1. Let's talk about these. These are called the standard unit vectors. And they have a special notation. They are denoted by I, and I is really bolded, and it's usually just a regular I. I kind of make mine look like a script I, but it's usually just an I like that. Okay, and it's bolded so that you can distinguish it from the imaginary, the number that we use for imaginary number I. So just make sure that you understand that if you see it in a textbook, you're going to notice that it's bolded, and that's so that you know it has to do with a standard unit vector, not with the imaginary unit I. So, and that's the equivalent of the horizontal vector 1, 0, and the bold letter lowercase j, which has to do with the vertical vector 1, 0, 1. These vectors can be used to represent any vector, v1 sub v2, so they can represent any vector as a unit vector. And so, for example, you would have a vector v1, v2, component form, could be equivalent to v1 times the unit vector, or v1 times the unit vector 1, 0, plus v2 times the unit vector 0, 1, which would be written with this notation. V sub 1 I, because remember this is your I, plus V sub 2 J. And these would be bold, J. Alright, and it would look something like that. Alright, so now let's continue to look at this, a little bit more information about this. It's a little, the notation here is what is tricky. The actual combinations of these and the actual operations of these is not too difficult. It's just that this notation is kind of strange looking. So you kind of have to practice a lot so that you get comfortable with the notation. So let's move on and continue to talk about these standard unit vectors. Okay, so now V sub 1 plus V sub 2 are scalars. And are called horizontal and vertical components of V. The vector sum V sub 1 I, no, I don't know why I make mine that way, sorry, plus V sub 2 J is called a linear combination. And I hear linear combo all the time. Okay, and it's kind of a big part of our vectors. We're now going to go through an example of writing a linear combination. So I'm going to show you that. Alright, so we're going to write a linear combination of a unit vector. I'm going to go ahead and label it that way. I'm going to write as a linear combo of the standard unit vector I and J. Okay, now I'm writing all these words out and using the terminology because that is what will throw you off, and you have to practice quite a bit to be comfortable with this notation. Alright, let's just take, for example, in this case, that we have an initial point. Okay, so we're not in component form. This is initial point of our vector at 2, negative 5, and we have a terminal point. Yes, I am. at negative 1, 3. And we could even graph that, and you could look at that on a graph. We're going to our first step is going to be, I'm just going to put step number 1 here, is going to be write the component form. And again, you just have to know what to do when I say that. All right, so we're going to write that. Remember, we're going to have our little arrows, and we would take our terminal point x, which is negative 1, and we would subtract our terminal point, our initial point x, so minus 2, comma, our y minus our y is how you're going to think of it, but the terminal first, so it'll be 3 minus negative 5, which is plus a positive. And all of a sudden, our component form then becomes negative 3, 8. And if we want to write it as a linear combination using the standard unit vectors, we have to now put these as this vector, the v1 and v2, we have to put it as our scalar, or our multiplier. So we could say that this is equal to negative 3 times I, the unit vector I, plus 8 times the unit vector j. And that would be our linear combination. So it's not that difficult, it's just knowing what the words and the terminology mean. Let's do another one. A couple other examples. All right, this is going to be vector operations. All right, so we're going to let vector u equal negative 3. This is a linear combination, I plus 8j. We're going to let vector v equal to linear combination I minus j. And we're supposed to find 2 times u minus 3 times v. All right, so the first thing we're going to do is we're going to do 2 times u. So 2 times, and our u is negative 3i plus 8j. And we're going to subtract from that 3v, which is 2i minus j. And remember, these are scalars, so we're going to multipliers. We're going to just like a distributed property. We're going to multiply through. We're going to get negative 6i plus 16j. I'm going to make those bold. And then we're going to have minus 6i plus 3j. And then we're going to combine everything, and we're going to get negative 12i plus 19j. Now, if we want to write that back as a component in vector form, a vector in component form, we would write it as negative 12, comma 19. Negative 12, comma 19. All right, that's mainly it for tonight. If you are pre-AP, if you are not, Bearcats, you can just ignore this second part. I need you to read page 453 to 455. I need you to work through in your notes. I want to see them in your notebook tomorrow. I want you to work through the examples within those pages, number 7 through 10. And I want you to have that in your notes tomorrow. It's very, very important that you work each and every one of those and understand them, and then you'll be able to practice in class what we need to practice. All right. Everybody have a great evening, and good night, cats.